Oh, yeah, the exam one data sheet was posted yesterday. So if you guys have any questions about that, please, this is a good time to ask, or Piazza is a good time to ask. I will have office hours today from 4 to 5. I'm going to be out of town on Thursday, so I won't have office hours then. I'll be out of town on Friday as well. If you need help in person, open lab hours are a good time. You can reach out to Matt and James. I'm sure they can be accommodating. As you know, exams are going to be this Friday from 4 to 6. It's going to be in this room, and the overflow room is just down the hallway in Dow 1010. People who need exam accommodations have already been contacted, so if I didn't contact you, please let me know. Please reach out soon. What else should we talk about? Any questions so far? Yo.
So the data sheet doesn't have any instructions on it, but like past data sheets did. Will we get that the reference manuals that are also there? Okay.
Yeah, the reference manual should be now posted. I addended it last night, and you'll have 2 different documents, so you don't have to bring anything. We'll give you copies of the data sheet and the reference sheet.
And the data sheet. Right?
Correct. Yep. What other questions do you have? Everything in that data sheet's crystal clear? Yeah.
So on the data sheet in the radio control register, I'm just seeing like a difference between what's in the picture and what's in the text. Like it looks like the send is corresponding to bit 1, but then in the picture it's bit 0. So I just wanted to see like which is correct.
Okay. Hold on. Computers are hard. Okay, let's see. You're saying that
Down. Yeah. So like in the picture it's showing.
Hold on, guys. I can't hear him. I'm old.
In the picture, it looks like bit 0 corresponds to send, and then bits 3 to 1 are the mode.
Yeah.
But then in the text below that, it shows bit 1 is send, and then bits 2 through 0.
No, it says that's the value. Oh no, is that? See, like here, we're saying that mod can be set to 111. It can be set to 000, and then that's the functionality that comes out of it. If you put a 1 in send in this bit over here in the 0th index of this register, then you're going to send data. If you put a 0, then it's just going to be ready.
Okay, I was just wondering because like on the left, it says bit 1 for send.
Oh, I see. That should be bit 0. They see that. This is like Google's pretty good. Okay.
And the one below should be 3 to 1.
3 to 1. Okay. Cool. We've redone our architecture like that. Fantastic. What other questions about the data sheet? I'm just going to take a note and post that on Piazza afterwards. Any other data sheet questions? Oh, okay, great. Okay. Any other logistics questions? Yeah,
I just want to clarify, there will be a data sheet there, we don't have to print one ahead of time.
correct. I'll hand you a data sheet, I'll hand you a reference sheet, and I'll hand you an exam. Yeah.
So we're not bringing anything.
Oh, here, all right, well, let's get to it, sorry. You can bring, this is the time, close notes, don't bring a notebook. You can bring a 4-function calculator, scientific calculator if you want. I don't think you'll need it, but why not? Not gonna hurt anything. No graphing calculators, no other electronics, phones in your pockets. We'll make sure there's a clock or a timer or something available in each room. So I guess it's that, but I'll ask Matt to put something up on the screen. Anything else? Yeah?
Is the reference sheet the same as the one from the previous exams?
As of today, so this is the data sheet. And here's the reference sheet is just below it. So you got Appendix A, Appendix B. It is the same.
Okay.
I noticed last night that some of the, I don't know, it's maybe a little out of order. So just make sure but it's the same reference sheet we've had the whole time. All right, great. So in general, don't spend too much time on any problem. Your goal is to maximize points. This is a game. The exam is going to be hard. You've seen the practice exams. The averages are usually in the 70s, right? This is just not a function of, we're not trying to punish you, but we're also trying to make it challenging so we can get a good distribution of grades. If you state all the assumptions, right? If you think we've made a mistake somewhere or something's not clear, we're going to grade you based on what assumptions you say. Like the counterexample is, I guess, if you totally restate, I assume this is a whole different problem, we're not going to find that valid. But if there's something ambiguous about the problem, you can just say what your assumption is and we'll work with you. Show all your work. It's unlikely that you're going to get partial credit if you just put an answer down. Yeah, data sheets. We'll make sure to update everything on Piazza so that things have changed in the data sheet. And probably like the morning of, we're going to stop updating the data sheet if there's anything comes up, just so nobody's like surprised. We'll just deal with the consequences. All right, so what to study? Homeworks, labs. Old midterms are on the website. Homeworks, where I try to be less ask you like all the trick questions. Like sometimes in 370, they're like, okay, if you really know this material, then you know this weird EDS condition that nobody's thought about in years. That's true. That would be a way to demonstrate you really know the material, but those edge conditions aren't really that important for learning the general concepts of embedded systems. So I would don't overthink things too much. Yes.
Is lab 3 part of the exam?
Lab 3 is memory mapped I/O? Yes. Yep. All right. So we're not going to necessarily cover interrupts. I mean, there could be a vague question that's related to the concept of things being interrupted, but nothing really in detail from Monday's lecture. Otherwise, it's ARM assembly, application binary interfaces, stacks and pointers, Kali safe, and memory mapped I/O. Really, those top two things are getting you ready so you can understand memory mapped I/O. The reason we're teaching you a lot of ARM assembly and ABI stuff is so it helps you when you get to interrupts in the rest of the class. You need that background information. So probably the most of the new material for you guys here is in memory mapped I/O. Yeah. So, hurry go through this. I never actually gave this lecture. This lecture was posted online. It's not that important, but I had a couple people in office hours saying, like, I don't understand what instructions are in the data sheet and how it's formatted and what it's doing. So we'll kind of go through that. So, these are the general structures that you saw or in 370. If you're trying to read the ARM7 manual, this thing is kind of like horrible, right, to try and decipher what it is. It's when you're an expert on embedded systems, then you're like, aha, it's super useful. It's very bad for learning. So just as a reminder, there's a mnemonic here. The S flag here is an optional flag that tells the assembler that this instruction should set the conditional flags, okay? So you don't have to set the conditional flags. This is just the mechanism that you could use to do that. There's a thing called conditional blocks. We don't really worry about them in this class. It's a nice way to set up basically case statements or branching statements. Not that important. Wide is the way to tell the assembler that this should be a 32-bit instruction. So you could write an assembly instruction that requires you to go to a higher register that you couldn't normally get to, and it will have to choose wide, a 32-bit instruction, or you could still have a lower add that only uses the lower registers and could fit into a 16-bit instruction, and you could still tell it to be wide if you wanted to. That's all the wide is really doing. It's just a method to tell the assembler what to do, if it has options. You have your destination operand, source operand 1, source operand 2. Then there's all these extra things sometimes in some of these commands. So here's a shift. You can make this an add and shift left, right. And then on the next page, it will tell you about how to use the type. So you would put in a code for the type to tell if it's a normal add or logical shift left, logical shift right. But there's extra text that you would have to read to understand every little piece. What else is there? I think that's it. So any questions on instructions and the data sheet? Yeah.
Sometimes you ask us like to do something in the shortest amount of instructions.
Yeah.
So in cases like, let's assume I had to do an add and then for some reason I need to shift it.
Yeah.
And I wrote add and then I shifted it.
Right.
Would you minus points because technically we could have done it in one instruction had we done it this way? Or would that be like acceptable because logically it's the same?
I don't know. It depends how I phrase the question a little bit. But like, are you responsible for knowing every instruction and every trick to get the most out of every instruction? It's probably not a good use of your learning experience, right? That's why we have compilers and assemblers. However, the counterexample is there are fundamental ways in which the processor works, which sometimes is good to know that, you know, like by demonstrating that you made it small, that you would demonstrate that you understand how the processor works. So like I can't give you a clean answer, just take away that you were not expected to read the manual and memorize all the weird idiosyncrasies of instructions. Any other questions? Yeah.
Maybe it's preference, but why do they use N and M for the source registers? Like, wouldn't it, is that just what they use or does it stand for something?
No idea. Maybe it's the nth and the mth, I don't know. Yeah.
Are there going to be any questions on the exam that ask us to translate machine code to assembly or translate assembly to machine code?
Those sound like good questions if I chose to put them on the exam. I mean, if I was going to do that, I would give you something that looks like this. I'm not going to have, okay, please remember the encoding for a subtraction or something. All right, any other questions? This is really your time to get as much information out of me as possible. I'll just go through and regurgitate the lectures I've already done. I already know the material. Yeah.
Yes, so how much are we expected to know how to use the flags, condition flags?
Like the IT flags or just?
I guess.
Oh, like, sorry, the S?
Yeah.
You know it now. It's not that important. It's not like, oh my gosh, do you know like every version? So, but it could help you optimize something. So it's good to know it exists and why you should use it. All right. So big picture stuff, right? There's 16 registers. They're 32-bit wide. We're not really worrying about the main stack pointer and the process stack pointer. This is used if you have like an OS on top of this, so like TinyOS could run on an STM32. But we don't really worry about that. And then there's the program status register, which there's a bunch of stuff in there that you need to know about. Primarily for this exam, it's going to be the status flags of your ALU. The like the base address and the fault mask and the control logic, that's not important, but those are the registers that you should probably know Memory is organized, remember? Okay, I can ask you guys. You guys should know this question now. We have up to 4 gigs of RAM here. How much, or memory space, how much is allocated on your device? And why? Approximately, let's say. Yeah. 3 gigs? Not in yours, not in your little one. Why is there not 4 gigs of flash or SRAM on your device, even though they've allocated it? Yeah.
It's because they want the other vendors to like expand on the other unallocated memory, and so like in the future they can like have some other peripheral.
Yeah. So part of this comes down to remembering what ARM's business model is. They're not trying to give you the one microcontroller. They're setting up an architecture that allows vendors the flexibility to choose how much SRAM, how much peripheral space they're going to need. So if you're a vendor that's making a very small version of a microcontroller, say it's only got 4 pins or something. These things do exist. You're not going to really need that much space for peripherals because you don't have that many registers in there, right? You only got 4 pins. How many D flip-flops do you need to address to manipulate those pins? So now you have this lower amount of peripheral space. You probably, if you're doing something small, you don't need a lot of SRAM. You can make that small. You don't need a lot of flash. So they allow the manufacturers like STM to change, and for different product lines, to change the space, but yet the code would be transferable, right? So assuming that it would still fit, but the code always starts here, peripherals always start there, external RAM would always start there if they were going to have it. Okay. Unified memory structure, yep. The other one that trips up people oftentimes is that there's byte addressing, right? So we have, this was 32 bits wide in this example. This is how we architect it, 32 bits, and then you increment by 4 address. So your address is increment by 4, and it's incrementing by 4 because there's the option to do byte addressing. So you could address just a byte at a time. Why do they make this option available to you? Why not just do everything 32 bits? It would make life easier. Yeah.
If you wanted to write something that's, let's say, 1 byte, if you have a word addressable system, you're wasting a lot of memory.
Yeah.
That one.
Yeah, that's exactly it. And because we're in a microcontroller, we're not in user application space. There are things that have small workloads. Maybe you have a sensor that's only an 8-bit sensor. Well, then you want to pack in that data into memory as efficiently as possible. You don't want to waste that extra time. So really it's workload optimization for the particular thing that ARM knows these sensors are going to be used for. Any other questions? All right, so then a lot of this is trying to link all this stuff together, right? So we got memory, you've got addresses, you've got your program stack register, you got registers, memory, and then you have these code elements that do different things. They had to do operations in different places, right? So we have move, which is, in this case, a move immediate. This is all in the register land, right? We're manipulating things in register. Loads and stores are ways that the core can talk externally from the core to memory or to peripherals. And then you have some logics, like you can use your sub here to set these flags, and then you have, I don't remember why I was pointing loop to code, but basically you have these conditionals and branch conditionals. All right, what architecture questions do you have? If I ask you architecture questions, are you ready? Yeah, you say, oh, you're very confident, I saw. Very confident. Okay, what guys? What questions I ask you? No, I'll ask you tomorrow, or Friday. That's what I'll do. I think the big idea of this class of what you should be getting your head around with memory mapped I/O is that you have a core, and you have peripherals. Remember, peripherals are just locations in memory from the point of view of the core. But there's a mechanism in which we have to go and interact with those things. And so the core talks to the APB bridge. There is a high performance bus in between. In this class, we just don't talk about that so much just because it adds so much complexity that you'll lose the value of understanding how the bridge works. So just assume for most of this class that the core talks directly to the bridge and the bridge talks to these devices. So when you do loads and stores, you're literally manipulating these lines to transport data to one of many different destinations. And the address defines that destination. So one of the ways to do that is literally with loads and stores. So let's see. So this is this example we went through before. So we have a load. We're going to take the value that's in, let's see, what are we doing? We're going to load in the value that's the address that's stored in R0. We're going to go out to that. We're going to grab that value and we're going to put it into R1. Oops. Yes. And then there's all this offset indexing. So now I can say, oh, I want to offset. So on the fly, you're going to go through and add 4 to this value. We're going to go up 4 index and grab that word. So here, we're going to put that in R1. Post-indexing or pre-indexing is you index it, you update the register, and then you go get the data. And post-indexing is you get the data and then you update the register. Why are we making such a big deal about this? Why is post-indexing and pre-indexing super helpful when you're talking to peripherals? Why have they added all this functionality in here?
Like one example is if you wanted to enable something for GPIO A and then you wanted to jump over right after and do B and then C, like this will automatically do that for you.
Yep. So kind of built onto that, usually we don't go across peripherals only because there's only so far you can jump at one moment. Right? I think it's 256 plus or minus, I think. But if you are saying I'm going to be at address, or I'm going to look at peripheral GPIO port A, well, there's a bunch of registers there. And so now all you have to do is I want to go to register 0. Okay, you can just use this address. But then I want to go up to register 4 or register 8 or whatever it is. And then you just keep this value in here and you're just moving. All you have to do is manipulate that last little bit, the immediate basically here, to get to that register. So it lets you do offset registering based on some base register. So it makes that easy. And the architects know how often that happens. It happens so often, they said, oh, we better give you this functionality. How do we feel about registers and indexing? Do you want to do a, oh yeah?
I have more of like a.
Yep.
I thought like the point of ARM was that we had a bunch of simple like instructions.
Yes.
So this feels like you're combining something like with an add. Doesn't it kind of defeat the point of ARM?
I think this is still considered simple in the wide world of microprocessors. Other instructions would be far more complicated and also like very much mapped to different ports. So this is considered simple. All right, would you like to do an example exercise on this? All right, fantastic. And we missed it from lecture 2. Now we get to do it now. Very exciting. Yeah, you probably need another one.
I'm bad.
No.
We're waiting for this.
Yep. All right. Yeah. No, let's see.
You can't use that. Go find it.
Yep. Yep. Did we run out?
Okay.
Oh, we ran out a lot.
I think there's.
I was bad at counting. I got you. Let's see. All right. Oh my gosh, we might be tight. All right, here we go. Thanks.
Sorry about that.
No worries. All right. Yes, done.
What's writing my name?
Here, I'll put these up here so you remember what the heck those.
But 156 is 9C, right?
You can do 90, so it's 98 by the way.
Yeah. Nice.
Load R1, R0, so whatever.
Yes, the first 152 is 98 index.
98 just goes into the story. How it makes sense.
R1.
I have to do it live. I'm not gonna waste.
Now you use an R0.
It's the only value in memory that has any contents.
98 or 0, not that.
That's the address.
So when you go to 6.4 version.
Then we just do that and then it adds.
It's not.
It's like the post. So it's gonna store it right back where it goes, plus 2.
First and then we'll maybe.
Oh, if you want to store the value of the address here, then
That's what I'm saying, store it and then we can.
Just right here.
Why I put that up there?
Yeah.
You have it on your exam.
It's gonna increment R1 to 66.
I might be dumb.
R1 is storing R1 into R0. And then it's storing R1
Other than bang,
it's an R0 and R1.
that's the only one I remember.
And then it increments it. Then it's pre-incrementing it, so it gets it to here. And then it actually stores it again.
So you increment it by 2.
And then it actually
I'm 764.
Yeah.
0.
and then
Still not worrying about the we're just trying to fill out memory. But
Me too.
64, hex is 64, and then we store into, which is where we were already at. It's just like storing.
Stays the same.
Yes, it's the same, but then we increment R0.
You have to redo the whole thing.
yeah, it is.
You increment R0 to 4.
What is PSR again?
but which half is it of
Up here, you increment R0.
You add the
Store R0. Yeah, so that's
and then you just change the. It's 2 then, and 2 doesn't go all the way.
First, 4. You divide it into 4.
And then you do 2 again, and then you reach here finally.
So if you had a branch with a conditional on it, branch equals you'd have to look for, or if one of these had an SLE.
Yeah.
But then it's
But like which half?
Right, 9-8.
Yeah, LDR
You're loading the whole word.
First you're taking this whole thing.
Yeah. So half if it's there's
Yeah.
and then if there's a regular store.
It's not going to that same address.
I think it's not.
Oh, because you're saying it's.
Which one are you explaining?
And then we pre-index by 2, so it's 4.
Yeah, so scroll it. R1.
Even fortune cookies month, right? Cause I think
It's 98 next. I thought it was 94 next. God damn it.
Wait, this store instruction, he's gonna put it in,
Right, so
he's
it's
gonna
gonna
put
do
it
the whole thing.
right back.
Yeah, that's what I
So it's not
thought.
gonna do anything.
It's not gonna do
Yeah, these
anything,
are
but it's gonna have to update.
pre-indexing by 2.
Memory.
The next address.
We run out of memory addresses.
That keeps me, my head straight.
Watch out for that.
It's gonna do pre-index and then it's also gonna increment, so this is gonna go to 9C.
And then here, but value or
Increment this.
Let's see. These are by.
So R0 doesn't end, this one is gonna do. He just puts R1. Is not common.
it's proposed increment 2. Yeah, that's what I think, but it doesn't change R0. Exactly.
It puts R1 into the address at R0.
But that's what it does.
What we know.
Wait, this one?
Okay, I'm an idiot. Okay.
Post indexing, so and then here.
What's that?
No, increments are 0.
4 is full, 6, 8.
I just got all the videos. I just want to.
R1, R0,
wait for this store.
it's like, so R0 is originally one into R0 and then
It doesn't do anything, but then you have to.
R1 already has that same thing.
I have A0
Yeah,
there,
so it's just
sorry, I thought you
writing
were
it
talking
back
about
to the same
once you
location,
move.
but then you have to update R0. And then the second
So this is like an
store
infinite.
It's gonna be
We're
what?
supposed to fill out memory
9C.
until we can.
9A.
So
And then 9C.
You add 4 to
It temporarily increments.
Yeah.
Second cycle. Pretty good at actually going through this.
Like, I get like it stores 2 and.
Yeah.
But then, how'd you get more?
Right. Oh, I'm understanding. Yeah.
Because the first one stores the same. Let's let it out. And the address after.
Yeah, but then doesn't this right over?
But then this down here adds 4, so this is like adding.
Yeah, so you add the 4.
So then you're in the next
and
one.
then this one would write over with it. So you'd only store.
And then it would just keep doing that.
Alright. Somewhere. Okay, cool.
He stored at this time.
Oh, I think you're copying 2 in.
It's just
You're doing 3 stores.
Let's see here. So what do the first 2 lines do? Yeah.
Move 152 and load 152 into register 0 and 1.
So we're gonna, and 152 turns into what hex number? That was painful to figure out, as somebody pointed out? Yep, 98. And so on the exam, well, that's one reason to bring a calculator, to make your life a little bit easier, but I'm gonna try not to make sure that you're test that you're really good at hex conversion. We're just gonna assume that you're all great at hex conversion, and we're not gonna test that you are. And so at the end of the sheets, there's a hex table at least to do a little bit of help, but I'll try to make the problem so you don't have to do fancy hex conversions in your head. All right. All right, and then what are you doing? Okay, so now we've gotten in R1 is that value, right? And what do we do with stores? What's this first store going to do? Yeah.
Store.
Yep.
So we would store it in R0. So in 98.
Yeah, it restores it right back where it was, right? Let's see if we can go through here. And then what happens in store in the next one? Yeah.
We're taking whatever was in R0, add it to 2, and then like go to that address, put it in R1, and also increase the value of R0 by 2.
Yep. So we're 2 forward now. And then the last one. So here we can walk through the cycle. So basically it takes 64, right, and puts it in. We had 64 in 98, and then we put 64 back in there, and then we put 64, we incremented, we put 64 in, and we increment. So here we incremented by 2 after we were done. Then we incremented for this line 2 before we did it. So that's how we got a whole 4 forward, and then we just incremented by 4, okay? And then we're gonna add R1 to 1 and R0 to, or we're gonna add 4 to R1 and add 4 to R0. So then we're going to increment that value, and we're gonna go back to start, or store, I mean. And so now, the new, after you run through that loop, those are the new values, because you've added 4 to that, plus you've added 4 to the address, so then you went to the next address. Yeah. And then you keep going and keep going. When do you stop? Never. You never stop. Okay? You can stop. You stop when your exam, when the areas of the exam have nowhere to fill out, you can stop. Yeah.
Why do you overwrite cycle 2?
Why do we overwrite it? Just as exercise for students?
No, sorry, not why. Like, I thought it gets incremented, so it doesn't get over it.
You mean the very first line?
To A0.
Sorry, A0 yet? It's just repeating what we did with 98. So 98, we took the value out in the beginning, and then we just stored it right back where we started. And then we went and incremented, and then we post-incremented by 2, and then immediate incremented, putting that value in 9C. And then we incremented by 4, putting the value in A0. And we did the same thing here. So when you get back to the cycle 2, we have the address A0 in there, but we're not going to actually put it into 2 or 2 more. We're going to put it there. We're going to put 68 in to A0, incrementing the value in whatever this is, R0 by 2. And then before we do this next line here, we're going to increment by 2. So that puts us ahead by 4. Yeah.
I have a question. So when we get to the end of the first loop,
yep.
The thing is the address is 9C and the value is 68, right?
The address is A0, I believe,
right.
And the contents is 64.
Sorry?
Isn't the address, somebody else can help me, isn't the address A0
Okay.
after the first loop? And then the contents of R1 is 60, oh, here is 68.
Yeah, I see where my mistake was.
Yep.
Yeah.
Okay, yeah.
Do you have the final values for the registers R0 and
Do I have final values of, no, because there's no final. We keep going forever. We're gonna keep doing this, right? Because this thing never ends. So what's gonna happen, if you just had this running on your processor, what's eventually going to happen? You're gonna run out of memory. In fact, you'll run all the way back through memory, come back over the top, and then you start executing whatever that function does, right? It'll think that's code space, and it'll start executing it. Yeah. All right, any other questions? Yeah?
What happens if we swap the
If I swap them? Well, this would do, so remember the difference between this is one, the top store there stores it and then increments by 2. And the bottom, in the middle store there, increments by 2 immediately and then stores. So what would happen is you would do a half word, you try to put a word on not a boundary, not a boundary, 32-bit boundary. Your compiler might throw an error. Or yeah, you'd be writing not on the boundary, and you should have done a store half word instead.
Yeah, so we have to worry about like not on the boundary, or it's always on the boundary.
Don't worry too hard. That makes me have to worry if I made the exam correctly. I don't want to worry. You don't want to worry. Nobody worries about that. And it's also just it's an error that your compiler, it's not like an illegal operation. Your compiler just throws an error.
Wait, is something like an interrupt would catch this, or no? It's causing.
No. I don't think so. Okay. Any final questions? Okay. Let's go through ABI stuff. So we talked about subroutines. They have to preserve R0 through R11 and the stack pointer. You should be careful with R12. R12 does not have to be preserved, but it's really used for other functions that are outside of this class. So you don't have to preserve it. I'm just saying that you might see a program that's manipulating it in weird ways one day. Specifically with interrupts, if I remember correctly. So you're going to pass your arguments through R0 and R3. You start with the lowest one, and you go, R0 is second operand, and R1, R2, R3. You could pass a 128-bit value that way if you wanted to. Your function just has to know that's how it's going to be taken. And then you can pass return values through R0. Typically, it's only R0 through R1, although I guess there's no inherent reason why you couldn't do the other ones. The convention, or you couldn't do R2 and R3, but the convention is all returns go through R0 and R1, starting with R0 for your first return. Yeah, keep word aligned, that's what it says. So you're going to use your space, your stack space. If your function needs to use more than 4 registers, then the function's job to preserve all those upper registers. And so you're going to use your stack space to put that there temporarily and then pull it back. And so these are the caller safe and caller safe. Again, R9 is this function that's used for threaded operation, or register is used for threaded operation. You don't have to worry about that. R12 is for interrupts and procedural calls. So you don't have to worry about that. All right. We'll go through an example. We did go through this example before, but basically we're going to have a function that calls a function, okay? We're just going to do sum of squares here. So in this example, we have assembly code. We have 2 functions. So here's the labels. And the labels, this is not a whole line. It's not a line of it's not an instruction. It's just saying that this thing points to the next instruction. That's all these things mean. So we have main up there, let's say. We have square and then quad. We have a stack, and then we have code. So remember, this is all unified memory. ARM doesn't care what's going on in there. And then you have your registers. So your stack points up at hex 20002000. Why is it just dashes up there? Why isn't there a number?
It's some other functions or programs.
Yeah, we're just trying to denote that there is data there. The stack pointer is pointing at that. That data is just not relevant for this particular example. So somewhere else, put data there. So it points at valid data, basically, yeah.
So I guess just to clarify, like, if we're using the stack pointer, we have to increment it and then write what we want to it.
It increments for you. But just have to remember that, say, when you go push something up there, it increments, puts data in. It's not going to increment where, it's not going to put data where the stack pointer is pointing. It's going to put to the next spot. Yeah.
I just want to clarify, so that address that the stack pointer has in that register right now, that's the first spot where you can throw data in, or does it doesn't need to increment first?
It increments first. Okay. That is where valid data is. Somebody else's valid data. The next location is, it's not necessarily unallocated, but it's not used. It's not it's not part of what's been kept track of if there's something on that space, if that makes sense.
Okay. If you pop data, the number will go up, or is it gonna?
Let's see, so the stack grows down. So you're gonna push stuff off and the values, the address is gonna get smaller, you pop and the address is gonna get bigger.
Okay, cool.
What is the ABI convention for the link register? Because it's not caller or callee saved, but we still need to like push and pop it to the stack in certain scenarios. So,
well, I guess it would have to be the caller has to save it, right? So if you're going to manipulate it, you have to push it to the stack. So we're actually going to see this in this case. So let's walk through this case here. So, all right, what are we gonna do? We're gonna start at move. We're gonna put an immediate move value of 2 into register R0. We're going to branch to a label. So BL is branch label. The label is quad. Remember, the labels get resolved into addresses when the assembler does its job. And so now we're going to jump to the label, which happens to be, to quad, which happens to be at this address here. So program counter is going to jump. And now what are we doing? So because we're doing this, we're going to branch with link wait, did I mess that up? Branch link register. So we're going to pull the link register, put it there so we know where we're going back to. And the program counter is going to go to BL quad. So the next instruction after that is B end. All right. Now where are we going to? Okay, we're going to push the link register because quad knows is going to call another function. It's going to call square. So quad knows that, and it needs to preserve the way back to main. So now it's going to take link register and push it up to the stack, and then the stack pointer incremented. So back to earlier question, stack was at 200, and then when we push the stack, it incremented first, going to 1FC, and put the value of the link register in there. Yeah. I was just stretching. Fantastic.
I've noticed that on some assignments, and I think some practice exam, that the link register is pushed, but then the PC is popped. Are those two like used interchangeably, or is there some nuance there?
So basically, we said there was some value in memory. You could put it back in the link register, but you want to branch. So just place it in a different location. So when it says PC, it's not doing anything with the current value of PC. It's taking the thing from the stack, which is the next return thing, and putting it directly into the program counter, forcing a branch.
Okay, I see. So it's just like use the link register to branch, but
right.
It's just the names are allowed to be different. It doesn't. There's no like knowledge. It doesn't see. Oh, I need to find the PC. It just sees the next address on the stack.
Yes, so the programmer knew that the thing that was in the stack was the next address it was supposed to go to, and then so it just directly put it into the PC.
Would that be the same as just doing BXLR?
Yes, although in that case you need an extra instruction to do it, right? So if it's on the stack, then you would have to pop it back to the link register, and then you do BXLR, which takes the link register and puts it in PC. So you saved a whole one instruction.
Okay, so just to clarify, instead of doing pop LR and then BXLR here, we could technically just do pop PC and it would work.
Yes.
Time to go over exam questions.
Maybe. I don't know. There's office hours today. What's that?
How much office hours?
4 to 5. All right. Let's keep going. So what are we gonna do now? We are at push, so we push that up. Then we're gonna branch next. All right, so here we're going to branch. And we're gonna go to SQ. So now the PC is gonna change and we're did a branch link register. So we're gonna save the next instruction, which is this address here, right? Then we're gonna go up to squared. We're gonna square two numbers. We're gonna BXLR, so we're gonna take the link register and put it into the PC, okay? Then you're gonna go to the next instruction, which was, and it is the same instruction, but, I mean, it's the same function, but different instruction, so we're gonna go do that. We're going to save the link register. And then we're gonna go back up to here. We're gonna increment R0. We're gonna BXLR. There, and now we're up. Now we have to, right now we don't have the correct link register to get all the way back. We had to save that. And so I guess you could have done weird things like, well, you could have saved it like in one of the other registers somehow, but the SAC is the appropriate place for that. And so now you're gonna pop LR. So you're gonna push that back there, and then you're gonna BXLR to exit all the way back to main. All right. Questions? Yeah.
That question, I promise.
That's fine.
If you push R4 and then R5, and then pop R5 and R4, it's not gonna be as intended in that case, right?
Correct.
Wow.
Why?
Because it's just the address, so R4, R5, and you're popping it R5, R4, right?
So you have to the way to rationalize why is R making your life worse, right? You put those in that thing and it swapped the order on you. Why did they do this? So the way to rationalize that is how is the instruction made? So the instruction does not keep order. The instruction just has 8-bit values, and it's just one hot encoding, and it says you put a bit here, I'm gonna put the 8th register or the 7th register, whatever the register number is. And so in that instruction, for a 16-bit instruction, there's no encoding the order in which. So it just goes from, I think it's from highest to lowest. Yeah, does that make?
The pops, or if you do them all at once.
I just started talking. I don't know what his question was. What was your question?
It was just like if it was like with a comma, like a list of pops, and it was just in the opposite order to where you pushed it.
That should work, right?
No. So the problem is the order at which, so you say pop, R1, R2, whatever the order is, it gets reordered.
Right, from highest to lowest.
I believe so, yes. And when you pop. Pop is the opposite.
Yeah, so pop orders it.
Yes. Yes. Sorry, I thought he was saying, sorry. Maybe I misunderstood your question. If, say you pop 3 things, and then you use 3 different pop commands later on, and those pop commands were out of order, then bad things will happen. But if you used, so the rule of thumb is whatever you pop is what you should push, or whatever you push is what you should pop. The same number of things, that way you don't get lost.
All same line though, because it's one hot, it'll be sorted.
Yeah. Okay. Yes.
Wait, so if you push a bunch of things and then you also pop a bunch of things, you don't necessarily about order.
You don't have to worry about the order as long as you push 4 things up and then you do the next exact same 4 things, you pull them down, right? That's fine. But say you put 5 things up, pulled 1 down, or you pop something, and then you pop the other 4, you better keep track. Now it's your responsibility to keep track of the order because it could be out of order. Yeah.
I don't know if I missed this, but I know you branch to the SQ function. Yeah, that doesn't, you said that updates the link register? Because you have to branch back to the quad function.
So here we've updated the link register when we popped or when we branched, but because we were within a function, we would have lost the link register back. So when a function calls a function, that function must, or the first function must save the link register so it has its way back home.
How does SQ know the correct way back?
SQ knows that its way back to quad because it used branch link, because quad used branch link register here. So it's used the link register to hold the program counter where the next instruction was going to be. So when you branch the link register, it just came into the next instruction. The problem is when you're here, that instruction is not, or that link register is not valid, so that you had to push it a copy of the one here to get back to main.
The original link register is fine on the stack. It's just waiting till the end. And then when you're calling a function within a function, that's all kind of taken care of with the branch link.
Correct. So if you're just doing one layer of inception, you're fine. If you're doing multiple layers of inception, you got to keep track.
All right. So then BX. Sorry. So link. Okay. All right. We're good.
Okay.
So then, if you're doing the pop PC, are you only allowed to do that when you know that you're going back to main? Because like, how would?
Well, you can do it whenever you want if you as a programmer have kept track that you put the correct link register up on the stack.
So I guess why would you not just pop PC? Like, why would you go through doing pop LR or branch LR if you could just do pop PC?
You all can make different choices. That's fine. Yeah.
Okay, thank you.
Okay. Let's move on. Have office hours. We can talk a lot about it. Fine. Memory map.io. So this is the new part of the course that in some ways you probably haven't seen before. So what do I want to teach you? It's good to remember the difference. Why is memory map.io different than port map.io? So port map.io is saying I have a special instruction that only does one thing. So imagine you had an instruction that was GPIO 1, and then you could put, you had a special instruction that said GPIO 1, and then you could say I want that thing high or low. That would be great, and that would always raise that, port A, whatever, GPIO 1. But now you have to have a special instruction for every one of these functions. It's faster, or it could be faster, especially if it's something complicated. You could have an instruction that says enable port A, output, pin 1, output high, right? So that would save you multiple loads to do that instruction. However, it's very specific and not generalizable. So ARM has gone with, let's make generalizable instructions. We're only going to use loads and stores. You as a programmer now have to be responsible for going through and knowing that when you're putting bits into particular registers, that has this other effect. But it's a very portable architecture, meaning that many people can repurpose it for other tasks. Intel architecture is only really going to be good at PCs or desktop applications because it's port mapped. Feel about that. Okay. So we talked before about the anatomy of a GPIO pin. We guys drew it out. We looked at the details of the actual one in your data sheet. But the idea here is typical. There's multiple registers in a peripheral. And so in this example, we have 3 registers. We have an input register, an output register, and a control register. The control register is changing the function of the pin between an output or an input in this toy example. So each one of those is a state holding element, and then we're going to concatenate those together to make a register. So for instance, all the GPIO pins are at one address for, say, port B input. So that's a register. And now you can get all of the input state of all of that port with just one read at a time. How are we doing? Okay. And then you have addresses again for outputs and addresses for control. So if we went to, let me jump ahead. If we go to this example, right, that is exactly this example. We have our bus. It's going to talk, these are 32-bit registers. The thing that's not shown here is that there should be a stack of n pins here, which are all being controlled. That's what's missing from this diagram. Otherwise, this is a memory location that you can talk to through your bus. And specifically, I guess I'm going out of order here, but here's an example of what you would see in your data sheet. Your data sheet is telling you there's a GPIO in register. It has an address. It has a reset value. Those are the pin maps there. You can put data into 0 through 16 or 15 on this example. It is read-only. It's not write. You can't write into an input port because this is fundamentally not how it's wired up, or not how it should be wired up. The data for this pin does not come from the bus. It comes from the external world, right? You're not going to have two things that write to that port or write to that register. So you only have one thing. So that's why it's a read-only. The other ones can be read and write because you could write data into the GPIO port, output port, forget what it is. You don't want to keep track of it. And then you could read out of it and said, which LEDs do I have on right now, for instance? Or you could say, I forgot which mode I've set these GPIO pins. Some of them are high, some are lows. I can read out of it to understand what those pins are. And so the other big thing that you need to get your head around is how the core goes. And so we didn't really talk about how the core actuates the bridge. Let's just say that happens, right? The core does a store, then these lines go high, low, whatever they're going to do. Messages get sent across these pins, this bus, and then into registers here, those registers I just showed you that you guys drew to control that pin. So understanding that whole data flow is critical for this class. What questions do you have?
But if you're like reading or writing to a memory location through the ATV bridge, is that instruction to cache at all, or is that?
There's no cache on this device. Just one unified memory. Why don't you, we'll take a little break. Talk to your classmates, come up with a question. What question would you love to ask me about memory mapped.io? I'm sure there's lots of questions out there. No, talk amongst yourselves first, then we'll do it.
Same cycle.
I do not know.
It's the one piece because a lot of like the diagrams he has is we don't use.
You're covering the first 28 steps.
But then sometimes
Makes sense.
The same address.
How would you be able to?
I think it would have has
This different than this here.
on the address and
All right, I heard lots of great conversations. What questions do you have?
If P ready is just when it's ready to be read from, or it's just ready for the next like instruction?
P ready goes high when, so you have the setup phase and then you have the, I think it's called the action phase. And so P ready indicates the peripheral says I'm either, the data is ready for you to latch on the next rising edge, or the data will be read or latched in on the next rising edge. So it's basically saying my action is ready to do the final task.
One cycle after ready goes high.
No. Sorry. No, that's not what it means at all. So here's just an example. So let's see. P enable is going to go, I have to advance one more time. So basically you're saying the action happened here. T3 is when data, whatever this is, I don't know if it's a write or a read, data got latched in. So this occurs and then the bus has the option to do something afterwards. Does that make sense? So here, it doesn't even matter. This is P ready up there. P ready showing the bus does not, or the controller does not care if it's high or low. This is the only time it cares, and it happens to be high. It is stating here that on the next rising clock edge, it is ready to do the thing. It does the thing, and then it gets deasserted, or it does not care. Does that answer your question? or your question, I don't forget who.
So are you kind of saying like after the action happens, it's not that important when it goes back down?
I am saying it doesn't ever have to go down, and in this particular example, this drawing is showing that it doesn't care if it's high or low. It happens to be high, and so there's some peripherals that are always high. Like if it's just a register, it will be done in one clock cycle. It does not matter, it's just high. But if it has to wait, it will be pulled low. And then when it rises, that's the indication that on the next clock cycle it will be ready.
Have we ever done an example, like in terms of a design that makes it so that P ready has to be low for X amount of cycles and it's waiting?
We had an example of what a wait state would be. I don't know if you had an exercise on exactly that. So one common way to do it is some magical peripheral. I think you saw this in one of the exams, right? Has a line that says if it's high or low, it's ready or not. And then that would be the indicator that the peripheral is not ready to finish its task. So in an exam situation, I'm probably not going to say, okay, invent yourself an 8-bit timer to keep track of 8 cycles or something horrible. I'll give you some signal to make it easier.
In general, when you start a bus transaction, does the address data, the write line, and the select line all trigger at the same time?
Yes, so there's a setup phase where address, write data, p-select, and p-data, or p-write data should be instantiated if it's a write. If you're doing a read, you don't care about p-write data, but there's a setup phase. And then p-enable goes high for the action phase. Maybe it's called the transaction phase. So some people are like, does it have to be like this? Like, I want it to be a different way. Great, write your own port or write your own bus, right? There's lots of ways it could be done. Just telling you how this one is done. And so there's a setup phase and then an action phase, and p-enable is saying, okay, all this data is ready. So it's a minimum 1 clock cycle. It could be multiple clock cycles. I don't know why the initiator could take multiple cycles. So this thing goes high, that one goes high, and then it's up to the peripheral to say, okay, I will be ready at this time right here to do a task. And it could stay low for a while until it was ready to do a task. Does that answer your questions? Okay. Yeah.
So to clarify, the P address signal, it's not all 32 bits there, it's just the last 8 bits that it sends over the wire?
It depends on the inner workings of how your ARM core device was made. So it is unlikely that there are 4 gigabytes worth of address spaces that it needs to go to. Therefore, having those redundant lines on your bus probably doesn't make sense. And so you could imagine there's a state machine. Here, which says, well, I know there's, say, only 1,000 possible registers, possible addresses, so I'll just reduce that space and I'll reduce the number of address lines. But for the fact of this class, and we're not going to get into the particular architectures, I just said it's 32 bits to make exam problems easier. You have seen some problems from previous exams where you just use 8 bits.
Yeah. Oh, I didn't see at first on the P address there. From the output of the APB drive, there are 32 bits. I thought it was always 8 bits. So
Yeah. You can assume it's, if you see an exam it's only 8 bits, you can assume it's the last 8 bits. Yeah.
Do we know like how many cycles after, like for the bus control signals that some of these are triggered? So go back, right? Yeah. So p-enable goes after two write cycles, 2 clock cycles. Is it always that case?
P-enable, there's a setup phase.
Yeah.
And this bus architecture says that these things must be instantiated, not the clock, but these things must be instantiated beforehand, so that you don't want things wiggling around when you're trying to do an action. So it says there's a setup phase and there's an action phase. So yes, there must be at least 1 clock cycle between setup phase and enable going high.
And P-ready is driven by the peripheral, right?
P-ready is driven by the peripheral, correct.
So if we hold that condition that P-write and P-address and P-enable are 1 clock cycle ahead, could I have started all of this on T0 or did it have to start on T1?
It could happen at any T. It was just saying that there was a time before, but that's not an important part of this problem.
So on an exam, like I can, as long as I hold those constraints, I can write it in any.
Right. So you could do like setup, action, setup, action, setup, action. There's no wait in between.
You said those top 3 signals need to be done during the setup phase. Is PW data not during the setup phase then, or?
Sorry. PW data would also need to be set up during the setup phase. Oh, we're running. All right.
The wait phase is just waiting for the peripheral to be ready, basically.
Correct. Peripheral could take time. Who knows what it's going to do? And the reality is sometimes the peripheral's on a whole slower clock, right? So it literally will take multiple cycles. And that is why if we get to here, this idea that there's multiple peripherals, remember they each have their own P-write data bus. So 32 bits or 32 bus for each peripheral going back here. That means this thing can take a while setting up this data. The initiator can go off and talk to some other peripherals and have a transaction back and forth. Maybe that peripheral's faster, right? And then it says, okay, well, when I get back to it, then I'll read this data out and then do my task. So this is how it allows this thing to be much slower than the other ones. Yeah.
I have a question on the metastability.
You gotta be really loud.
Metastability and the D flip-flops on the homework, and why there was 2, how to set up.
So metastability, why is there 2? So a bunch of electrical engineers got real worried that if you were clocking in your data, or data was changing when you're clocking in, and there's an edge condition, if you look at all the circuits, where the circuit can literally get jammed between a 0 and a 1. They're like, oh no, if that happens, bad things will happen to my circuit. And they're like, how often does this happen? They're like, not very often. And then they're like, but it still could happen. And so what they did is they said, put 2 D flips out there, and that eliminates the problem. And if you're a medical device, you put 3 D flip-flops, because statistically, it's unlikely that in-between edge will propagate through your circuits through 3 D flip-flops.
If you add 3 or 2, that still adds a delay, right, or no?
Yes, it's going to add a 1 cycle delay to each one. And then you might come back and say, argue with me on an exam and say, it was only 3 clock cycles out, and you're trying to figure out when the human pressed the button. Does it really matter? So you have to kind of figure out, is 3 cycles latency important?
So on the exam, if we have to read some input, do we need to have the flip-flops or
Under what conditions do we need to worry about metastability?
Very high-speed digital electronics and medical devices.
Yeah, but there's a specific case.
Asynchronous clock.
Yeah, so if you have 2 clock domains, they're not synchronized. Because if your edge always comes away from the clock transition, or sorry, if your data transition is always guaranteed to be away from your clock edge, it never happens. You never have to worry about this. But if you have some asynchronous device over here, like a windmill or something, that's going to throw in edges whenever it wants to, then there's a probability that something bad could happen. So if you see a clock synchronizing 2 devices, you probably don't have to worry about it. Yeah.
I'm sorry, was the answer to that because there's 3 total D flip-flops between the asynchronous clock signal.
Yeah. Let's see. I see a lull in questions, so I'll try and teach this last little bit. It's important to remember conceptually that there's different peripherals, and remember peripherals each have their own p-select. But in any individual peripheral, there could be multiple registers with multiple addresses. It could be hundreds of registers in a peripheral. So that's why you really need to keep track of the adder or the address. Now the challenge here is that in your exams, it's very hard to write out 100 registers and have you write up 100 registers. So most of the examples that you've seen only have 1 register in there. But I just want you to conceptually know that there are multiple registers in each one of these peripherals, and that's why the address is actually really important, because you need to be able to specify where you're putting data into. Even though sometimes in the examples we just say, it doesn't matter.
So
So like on those problems, if there's an address, like so would we have to like write P address to anything if there's only like one register? If we just wrote P.
Yeah, you probably want to look at the problem definition, and it might say, if the problem definition said, hey, this is one system block of a multi-block peripheral, and you have to worry about masking for addresses, then that would make a difference. But if we were vague and just said, hey, this is a peripheral, you're making a peripheral, and there's only one address in there, then P-select is going to do the selection for you. So think about P-select selects like the global set of addresses, and then address does the individual addresses inside that global selection. So it's kind of these two stages. That's all I want to teach you. Yeah.
Going back to the D flip-flop, is the asynchronous clock the biggest use case for that, or are there other like design considerations and like why I would want to use a D flip-flop?
Yeah, it's usually that there's asynchronous clock or just asynchronous events. So something could happen on a clock edge, and that could cause metastability. So if things are synchronized with a clock, you don't have to worry about that. Yeah.
Could you explain like what all from digital circuits, like analog circuits, do we need to know? Like the open drain and like the push-pull stuff for GPIO.
Yep. You need to know that.
Could you explain?
Oh, could I explain what it is? Oh, you want me to teach you things? I don't know. Okay, what do you want to know? So it would be good to review lecture 1. There's some false data. There's the links in there. You see weird links. If you take the whole link and put it in your browser, it will take you to a circuit simulator, and you can play with it. You can see, you need to get intuition about how a MOSFET works as a switch. I'm never going to ask you to calculate like the transfer function of a MOSFET. I did it once when I was undergrad. Don't need to do it again. I don't even want to do it. But knowing that if you put ones and zeros into a MOSFET, that will let current go through or not, that's important to know. So that's my general spiel. If you have a specific question, I'm happy to answer it. That's good? Okay. I'll say this. From a studying point of view, if you know this circuit and can get your head around this circuit and how making this a 0 or a 1 will change the output here, you're doing good. This is usually ground. And then, if you want to understand open drain, you just take this part away, okay? And then you're like, you know what I really want to do? I really want to make this thing high. There's no way to do it. You cannot force it. You can pull it low. And so sometimes we'll do things like put a resistor here. And so the resistor will pull this thing high. How does it do it? Well, it says, basically, if there's no current through here, so say there is no current through here, then this voltage on this side, the voltage across this would be 0, therefore this voltage and this voltage are equal. And then if there is a voltage here, then there's some current trying to pull this thing higher and higher and higher. So the result is that if this thing is open, if the switch is open, then this is going to be VDD. And if it's closed, it's probably going to be a stronger short than this big resistor, and it's going to pull it down. So if you can just intuitively play with Falstad and just learn what this circuit's supposed to do, you'll be fine. Yes?
Well, if they're on the exam, be drawn the way you just drew them and not with like the arrows pointing up or down or like the other.
Oh, you want me to be consistent? That's tough. So this is like how digital logic people do it. It's like the old school way. And then the other way that we're talking about is PMOS is up here and NMOS is like that. I think the best thing to do if you see confusing things, come ask during the exam. But it should be probably self-evident by the structure of what it's trying to do. I'm not going to like put the NMOS on the top and the PMOS on the bottom just to make your life worse. It's probably going to be in that order. Although if I taught 215, I would do that. Or 216, 316. All right, any last questions? All right, thanks.
There you go.
Yeah, just the right side to go, I guess, high.
I think the output on this doesn't matter because I don't know why you would need to write.
The one where they make the straw.
Like this arrow is. You would never be wanting to put
Dude, what did you do?
It's
like a way of reading. It's like
Correct.